Hello, it's Martin from Wisely Automotive. Please excuse all the background noise, but this is the joys of filming in London on a Monday morning. But I am here with two cars for a highly requested video. We have promised in the past that we would do a heat pump comparison to see how much more efficient the heat pump cars are in real world conditions compared to cars without the option fitted. So these are the two examples. The grey one is the one with the heat pump. The blue one is a standard 120 amp hour with just the standard PTC heater. In terms of battery degradation, they are very similar. One is showing 97, the other one 98% state of health. One is older, the other one is slightly higher mileage. So this is about as close as it gets. And most importantly, they are on the same wheels. To see the difference when they are being driven as well, not just sat here static with the heating on. Speaking of which, let's discuss the setup. Both of them have been left outside for the entire night. It's a particularly cold morning. It's only 4 degrees Celsius out right now. So they should be nice and cold, even temperature on both of them. We will double check that in a second because I've plugged OBD dongles into both. And the plan is that I will start preconditioning on them at the same time. Preconditioning from the key fob or from the phone app only starts heating the cabin. So that should be the most accurate way of telling how much energy they use. Both have been left at 100% state of charge, and we will see how far they drop. From the OBD data, we should also be able to look at the interior temperature. So without further waffling, let me get the apps and we can get started. It just ticked onto 8:20 a.m. So let me put this down for now, and I will use the diamond button on the key fobs to start the heating. So both of them, let's see, they should be on right now. So the heat pump car is definitely running. There's a little fan icon flashing on the HVAC panel, and the blue car is running as well. Perfect. So let me look at the data. I need to make sure I don't confuse myself because I've got two cars in front of me right here. As I said, both of them started at 100% state of charge. And if we look at the battery temperature, they are within half a degree of each other. So that should not make any difference either. State of health, as I mentioned, super close. Outside temperature detected at 5 degrees for both of them. And so far 10 degrees on the inside. I'm not quite sure how frequently that inside temperature updates and where it's measured, but we will figure that out as we go. And most importantly, what we can see now is that the heat pump car, you would expect it to be a bit more efficient, but in fact it's pulling more power than the car with the resistive heater. And this actually makes sense, and I will get onto that in just a second. I can also hear the heat pump car running. Heat pumps basically are compressors. And if I move my mic closer to the back, I don't know whether you can hear it all over the background noise, but it is definitely running. Whereas this car without the heat pump is absolutely silent, but I can see in the cabin that the air conditioning is running. With the preconditioning from the key fob, both of them are set to the same temperature, so they are running on identical settings, regardless of what you had previously set on the air conditioning panel itself. So this is interesting. The heat pump car is still pulling significantly more power, about 5 kilowatts, whereas the PTC heater is only taking 2 kilowatts. As I open the doors, they're definitely nice and toasty inside, and I would have no problems driving in either of them, even just after 10 minutes at 5 degrees Celsius outside. And after 11 minutes in, the interesting thing has happened, that the heat pump has officially dropped in power below the car with the PTC heater. So the PTC heater is staying constant, pulling about 2.6, 2.5 kilowatts of power, whereas the heat pump is now hovering between 2.3 and 2.5. Occasionally jumping down as low as 1.6 kilowatts. And the cabin temperature on the vehicle with the heat pump is a couple of degrees higher. And in fact, it's rising very quickly. As I've been speaking, it went from 15 to 17 degrees Celsius. About 15 minutes in, and heat pump below 1.5 kilowatts, literally pulling 3.5 amps, and that's virtually nothing, because you have to keep in mind that even running the onboard computer and systems takes a couple of 100 watts. The heat pump itself is probably using only about 1 kilowatt, whereas the PTC heater is still hovering around 2 kilowatts. And temperature-wise, the cabin on the heat pump car is still staying ahead, about 3-4 degrees ahead of the PTC car. A couple more minutes in, and the blue car finally dropped below 2 kilowatts of power, and the cabin is now up to 17 degrees. but on the grey car we are already up to 20 degrees Celsius, but still using the same amount of power. Exactly 20 minutes in, and the heat pump car has officially hit 22 degrees Celsius in the cabin. PTC is quite far behind at 18 degrees Celsius. And power-wise, more of the same story. Heat pump has dropped down slightly, but it is oscillating. Now the heat pump jumped to 1.8 kilowatts, so quite similar to the car with the PTC heater. But with the heat pump, what I have noticed is that it seems to do a few short bursts, you see, because now it has dropped back down to about 1.2 kilowatts, whereas the car only equipped with the PTC heater is relatively constant between 1.6 and 2 kilowatts of power. And as you just saw on the grey car, the temperature keeps flipping between 21 and 22 degrees Celsius. So at this point, I'm fairly sure the system is just trying to maintain the target temperature of 22 degrees. Not only based on the power, but it has also gone much quieter than before. Another interesting crossover point just happened, because if we were keeping an eye on the state of charges, because of the initial burst of the heat pump, it obviously burned through a lot more energy. But now that it's only maintaining the temperature and it's sipping power, it is finally at the same or slightly better state of charge than the blue car. We are literally splitting hairs here because both are showing about 99.2%. But don't you worry, we will double check those figures in just a second. We will not just rely on the BMS reporting the real-time data here. 25 minutes in and we are getting close to the end. Heat pump is now settled at about 1.25 kilowatts. The PTC has settled at about 1.7 kilowatts of power. So this is realistically where you can probably see the difference, that once the cabin is up to temperature, the heat pump is slightly more efficient. But looking at the difference between the state of charges, it's still very, very small, only about 0.1%. The blue car is still only at 21 degrees, whereas the grey car with the heat pump has now jumped to 23 degrees Celsius. Also, this is a good opportunity to mention that neither of these have been fully prepared yet, so don't judge the condition too much. By the time this video goes out, the grey one will probably be up on sale on Auto Trader, whereas the blue one, that's more of a project car and it will feature in one of the future videos. So stay tuned for that, because we think it will make many people happy. Yes, that's it. 30 minutes gone. We can see that the power has settled in both examples. One of the questions we often get asked is, oh, what if I get stuck in a traffic jam? Well, you can see based on the values in this kind of idle state, even with heating set to 22 degrees Celsius, you can be running both of these for hours before they deplete from 100 to 0. I will put the exact number on the screen now so you can see the difference for yourself. But generally speaking, it's not something you have to worry about at all. I think that's about it. Not much more to show, other than the fact that we have also kind of inadvertently proven that battery heating with preconditioning from the key fob or from the phone app does not occur, because as you can see, the battery temperatures are pretty much identical to what they were when we started. The state of charge is extremely similar, but as I said, to make sure that we get the numbers as accurate as possible, I will plug them both into the Hypervolt, and we will get a metric from the Hypervolt and from the My BMW app about how much charge they take on to get back to 100%. But that's not all, because we will also attempt to road test them to see the difference in driving conditions. Now you may be a bit curious about how it actually works behind the scenes, because often when you read about heat pumps, it seems almost too good to be true. With normal electric heaters, it's kind of obvious. You put some electrical energy in and you get heat out. And generally speaking, they are almost 100% efficient. Meaning if you put 1 kilowatt of power in, you almost get a kilowatt of heat out. Normally with electrical systems, when we talk about losses, they're generally heat losses. But in this case, heat is actually the product we want. So it's a good thing, hence why the almost 100% efficiency. And that begs the question, how can you better 100%? That's where heat pumps come in, because no, they do not break the rules of physics. They just use the laws of nature in a very clever way to work smarter rather than harder. Specifically, they leverage the fact that temperature and pressure of fluids are very closely related. A very easy example from day-to-day life of this is if you have a car, you may notice that if the weather suddenly starts getting colder, the tire pressure will also drop. And vice versa, when you start driving and the tires warm up, the pressure will go up as well. And this is utilized at a slightly different temperature range to move heat from the outside environment to the inside. And move is the key word, because at this point we are not using electrical energy to generate the heat, or convert rather the electrical energy into heat, but we are using it to move the heat across. as anything technical, this is best explained with a sketch, and I will try to make it as intuitive as possible. So let's start with the outside environment. Let's say it's still about 5 degrees outside, and we need to get heat into the cabin through some fluid medium. In the context of automotive heat pumps, the medium is usually the refrigerant gas, just like in the air conditioning system. This refrigerant can go down to very, very low temperatures. So in comparison, those 5 degrees in the environment are actually quite warm. All we need to do at this point is to provide some sort of a heat exchanger like a radiator, and nature takes over with the heat moving from the ambient air into the medium, trying to get it up to equilibrium with the temperature of said air. Of course, the maximum we can reach at this point is 5 degrees Celsius, and that's still far too cold to heat up a cabin, which we want at usually 22, 23 degrees Celsius. So the refrigerant is now passed through a compressor, and remember, that means it increases the temperature as it increases the pressure, and suddenly we have a refrigerant which is very, very hot, much warmer than the desired cabin temperature. So again, we need to provide some sort of a heat exchanger and let nature do the thing with heat flowing from the refrigerant into the ambient air. This means that the refrigerant cools down slightly, but it's still far too warm compared to the outside temperature. So to complete the loop, an expansion valve lets the gas expand again. And remember, expansion means a drop in pressure, hence drop in temperature. So the loop can keep on going to maintain the temperature you want. And now when you step back, you can see why a heat pump can be so much more efficient. It's because the only energy we are putting in is the electricity to drive the compressor. The rest is just laws of thermodynamics, which in practice means to get the same 1 kilowatt of heat in the cabin, in these automotive applications you only need to use 500 watts of power, or in other words, less than half of what a resistive heater would use. And even though it may sound like this brand new technology which is not proven yet, it's something we have been using for decades in the form of air conditioning or refrigerators, which follow the same principle, just with the outside and the inside environment swapped, which is keeping a confined space cold and dumping the heat into a warmer environment. With that little lecture over, let's look at how the heat pump is actually integrated into the i3, and we will start with this blue example, which does not have the heat pump, to establish sort of a baseline and work up from there. To gain access, I've removed the frunk, which is really, really simple. That gives us a view of the gubbins and the electronics under the bonnet. So I will do my best to get you close-up shots and extra diagrams so you can actually make sense of what I'm talking about. Luckily, the cabin heating system is fairly simple because it consists only of a single coolant loop where the coolant acts as a medium to move the heat into the cabin. It is the squarish black reservoir on the right side here. And if you look further down the thick lines, it connects to the electrically powered heater. If we were to disassemble it, it literally looks like a glorified kettle with a submerged heating element. And there's also a 12-volt pump, which just keeps the fluid moving. Because on the other side of the system, there's again a heat exchanger. You can imagine it as a radiator with a blower fan moving air past it to get the heat from the warmed up coolant into the cabin air where you want it. As you can probably see, the only way the high voltage system is involved is to power that electric heater. What I'm trying to say is that the traction battery, even though it is electrically heated, with a bit of a caveat, and that is that it's only heated on cars equipped with the cold weather package, which is easy to spot because the other option it includes is heated seats. The drive battery heating is completely independent of the cabin heating. So even though you may have a car equipped with the heat pump, that does not improve the efficiency of the battery heating. That heating system very closely resembles underfloor heating in your house, but in this case it's all handled electronically through a heating wire laid out in the floor of the battery tray. With that covered, let's see how the car with the heat pump is different. It still looks very, very similar, but if you look very closely, there is a bit of extra plumbing in the middle here. And you will be able to very clearly see, especially on the diagram, that the core of the system is the same. So even though the car has the heat pump, it still has the high voltage electric heater. It's just that the loop is extended with an additional heat exchanger to facilitate the transfer of heat, which is generated by the heat pump, into the cabin coolant loop, which we can see here under the bonnet. This is simply because of the nature of heat pumps and the fact that they take usually a bit longer to heat up than a resistive heater, which is pretty much instant, and also their operational conditions are much more narrow. So if it gets very, very cold, especially below freezing temperatures, the electric heater will need to pick up most of the work. The nice byproduct of this is that you essentially have a redundant system, because either the electric heater or the heat pump, or in other words, the air conditioning compressor can fail and you will still get heating inside of the cabin. And we have seen this from experience that sometimes if you keep your heating on very low on a heat pump car and the electric heater is broken, it will provide the heat happily, but the moment you crank the heat up and the heater also needs to engage, you will get a drivetrain warning. It's BMW making the situation a bit confusing, but in their mind, drivetrain means high voltage system. I don't know about the rest of the world, but at least here in the UK, regardless of which system you have, the car uses the same R1234YF refrigerant, which is listed on a sticker under the bonnet. So how do you determine whether a particular car has a heat pump? Well, rather than disassembling the front section of the car and looking at the individual components, which you can see the heat exchanger, and for example the additional refrigerant reservoir in the corner here as well, the easiest thing to do is to just go onto a website which can give you the entire specification of the car. If you're buying from us, we do all of this work for you, so we can exactly advise you which of our cars in the portfolio have the heat pump. But if you're doing this yourself, you can just put the VIN number in, and the code for the heat pump is 4TANGO9. So if that's present in the list of optional equipment, the car does indeed have it. If it's directly translated from German, it can be referenced to as the auxiliary cabin heater, but rest assured both of those things mean the same thing. The last technical thing to mention is why the range extender cannot be equipped with a heat pump. And that's because if you look really, really deep down under the bonnet, where the heat exchanger is on the car equipped with the heat pump is exactly where the 9-liter fuel tank and the fuel pump lives to feed petrol into the range extender engine. So I'm afraid even though it would be a lovely combination to get the maximum range out of an i3, it is not possible. You can make the case that, for example, if BMW relocated the tank into the front storage compartment, it would have been possible, but there are still some lines running along the side of the car which probably would have interfered, and it would just create a complete mess in the manufacturing process because you would need to have dedicated parts just for one version of the vehicle. So I'm afraid this is what it is. We just have to take it as a fact. Likewise, trying to retrofit the heat pump, it's a question which we get asked about a lot. It's practically impossible because not only are you extending the cabin coolant loop, but also the air conditioning loop. There are additional valves and the software would need to be recoded, so it's not something anyone would do for you. Okay, so test number 2 will be the driving bit. It's after closing time, but it's very difficult to find a quiet time for us and on the roads for the consistency of the test. So I managed to rope Arthur in. He will be driving the non-heat pump car.
Yes.
I will be driving the heat pump car. You are just doing the tire pressures.
Yeah, so we're going to get them all factory settings. So 36 on the front, 41 on the rear.
Perfect. And they've got the same wheels, same tires. So again, we're trying to make the test as consistent as possible in real world conditions.
Yeah.
Both of them I've topped up to 100%. They've been left plugged in again for a while for the batteries to really reach full 100%.
I can confirm I've seen them charging away all day. Temperature wise, they're both
exactly when we set off, we can double check from the OBD readouts that the batteries are roughly the same.
Cool.
And it shows the cabin temperatures as well, so that's the best we can do.
Anything else we're missing?
The last thing which we will need to do is balance the weights.
Can you hide the result, please?
Of course. We will do a nice close-up of that.
No, none of that. Okay. No.
I gained weight.
So what's the result?
30 kilos between us.
30,
so
okay.
How many wheels is that?
We're doing two 428s. Boom. There we go.
Perfect. I've got 8 degrees outside, 11 inside, so that's close enough.
I've now got 8.5 and 11. I guess it's because we're sitting in here a bit.
And go into your driving information and reset the trip computer.
What are you doing?
I'm trying to set up the camera. Okay, you get going.
You sure? Oh no, Brenzen's gonna block us in.
No, he will not. Let's turn on the HVAC on. I'm actually starting to fog up a bit, so let's do, as we discussed, automatic with fan strength 2 and temperature to 22 degrees for now.
Okay, so we're trying to keep as close to coasting as possible, yeah?
Yes, coasting and just gentle driving because we want to see the effect of the heating on this trip. But when we are stopped here, check how much power you are pulling. So under battery power, that's the first item when you are sitting still.
Yeah.
how many kilowatts is it showing?
Minus 2.16, minus 2.32.
Okay, because my car's only pulling about 1.7 and it's really like it's getting warm.
Yeah, no, mine's getting warm. I'd say mine's getting warm now. But mine's drawing now minus 2.47.
Okay, so about half a kilowatt more than mine.
Which kind of makes sense if the heater's having to work harder.
We managed to stay together even through the London traffic, and we joined the A2 heading southeast towards Dover. Initially the speed limit is 50 miles per hour, but we set our cruise controls to 65 right as we get to the section with the national speed limit. Arthur also makes a good comment about the driving conditions.
6 degrees outside, so I'd say a very kind of common UK winter temperature.
And this should be close to the sweet spot for the heat pump, because if it's too cold, the heater has to kick in anyways, and if it's too hot or too warm, you won't see much of a difference. So like this is about as significant as it should be. Right around Rochester, we get off the motorway and turn around. Even though the wind speed is very low, making for good testing conditions, we keep a large gap between us to avoid any aerodynamic benefits, and we swap our positions in an effort to keep it as fair as possible. A couple of minutes later, we pull into services along the route to compare the stats. What does your trip computer say?
I've got average economy so far 3.8.
Same, exactly 3.8 as well. And what's your battery state of charge?
I'm on 76% dead.
I am 76.5. What's the app showing? How much power are you pulling when you're stationary now?
So right now it's fluctuating a little bit, but roughly speaking it's 1.68 to 1.77.
Okay, so I'm pulling 1.32, which makes sense.
That is it's just it doesn't really translate to, it doesn't seem to translate to long distance improvement. Well, so far 0.5%, but
Well, yeah, because if you think about it, most of your consumption when we're driving fast is to the drivetrain, not necessarily for the heating, so it's a very small fraction.
do you want a chocolate bar while we're here? Oh, I forgot you're vegan. Damn it.
Without any snacks, we continue back on the same route and we enjoy the, by London standards, quiet roads. So we have officially arrived back to the showroom. Arthur has been refusing to state his state of charge for the second half. He just wants to keep it a surprise. So I will show you my side of things. If I turn the car on, that's reporting 64% on the dot. The My 3 app is a little bit more accurate. It gives you accuracy to 0.1%, so we've got 63.7. And if we look at the trip computer, this heat pump example has averaged 4 miles per kilowatt hour, 61 miles covered in 1 hour and 46 minutes. So with that said, let me get out and let's see what Arthur is at. Hello.
Hello.
Spill the beans.
No. What's yours?
60.
Yeah, go. I know that bit.
3.7.
Points. It doesn't even read in 0.7.
You can use the app from the OBD.
All right. Okay. Well, you ready?
Yes,
Firstly, what was your distance?
I forgot.
Okay. I'm sure that they were the same when we spoke
Yes.
a few minutes ago.
It was 61 miles something, yeah. 63.0.
There you go.
Mine is showing the same 4 miles per kilowatt hour as yours.
I think it's very interesting how the gasometers have kind of
Aligned themselves.
It shows that it definitely takes about 50 miles of driving for it to kind of learn a driver profile.
Yeah.
And it shows that we drive quite similarly, which I'm shocked by.
63.1%.
And you said yours was 63.7?
Yes, I think so.
Oh, wow. That's an interesting...
That's very close, isn't it?
Yeah. We've kind of proved that using 37% of the battery in cold temperatures on the motorway, you can do 61 miles.
Yeah.
I've just done some very complex maths.
Yeah.
165 miles.
Yeah, the range is very good.
Yeah. But yeah, have you told them about this car, by the way?
Briefly. So go on.
Well, no. I'm not sharing it. But the next time they see it, it'll look very different.
Very good.
So, cool. Well, over and out.
Yes, so as Arthur has said, I will let him go home now, and I will pick up the numbers tomorrow. We will go through everything and we will summarize what we have learned today. Let's go back and start with the static test. I've got my iPad so we can go through the numbers together. I will put everything up on the screen so you can draw your own conclusions. And instead of going through everything one by one, I will just highlight the important message. As you can see, both the cars dropped by about 1.5% state of charge, and depending on how we calculate how much energy was used, we are looking at about 0.6 kilowatt hours for both cases. The heat pump was a little bit more efficient overall, but the PTC heater only used about 7% more energy. I am going to discard the numbers from the Hypervolt in this case, because when I started charging, I set the charging mode to Eco, which limits the charging current to 6%, but then I realized it would take forever to charge both of these and complete all the tests, so I bumped it back up to full 32 amps for 7 kilowatt charging, but that may have caused a little glitch in the software, or the car was doing some sort of cell balancing at 100%. So with those two values being so far apart, we can't really consider them. Next up, the shocking thing was the heat up time, with the heat pump getting to 21 degrees in 18 minutes, whereas the PTC took almost 26 minutes. And this is the really kind of substantial difference we are looking at. Likewise, the peak power. I know some of you may be very skeptical about how is it possible for a heat pump to use more power. Well, the numbers actually add up very, very nicely. The PTC heater in the i3 is rated for a power output of 5.5 kilowatts. And as we discussed, when the i3 is idle, the computers and the rest of the 12-volt network uses about 250 watts. So that exactly adds up to the peak we got on the PTC. With the heat pump, we obviously have the 5.5 kilowatt heater, and on top of that, the air conditioning compressor can draw up to 4.5 kilowatts, but I doubt it would go for full power in case of the heating, especially with the initial boost of the PTC heater. Once the consumption leveled out, we are looking at about 1.25 kilowatts of power for the heat pump car and just under 1.7 kilowatts for the PTC heater. So yet again, proof that the heat pump was working and it is more efficient. It just would need to be in that state where it maintains temperature for a very long period of time for the difference to be really, really noticeable. Speaking of which, let's move on to the driving test, where we set off with 100% in both cars and use just over a third of the battery in both cases to complete the journey. Just as before, there are many different ways of looking at exactly how much energy the car used, but I think this just proves that now with reliable data from the Hypervolt app, the deviation is really consistent with the estimate based on the Kappa Max, and this makes sense because the cars can have slightly different battery degradation. At the end of the day, we are comparing two different vehicles. Don't be alarmed by the fact that the car is reporting a lower figure than the charger. There are always some charging losses, and as we saw, the state of charge indicator on the i3, especially at the top end, is not very linear, where it sometimes may stay at 100% for quite a while before it starts dropping out. And it's the same scenario with the energy going into the battery, where the cell balancing needs to happen at 100%. I forgot to mention that when we got back, we did double check the battery temperatures, and again, they were very consistent between the two cars, so no advantages on that front. The big takeaway is that after driving 60 miles and using 36% of battery, the difference between the heat pump and the PTC was only 0.6% state of charge, which really is within margin of error. And I know even if you say that our test wasn't perfect, and there may have been differences, and even if we double that number to about 1% difference, that's 3% when we consider the entire range of the battery from 100% all the way down to 0. So with the 160 miles of range we got, 3% of that is what? Less than 5 miles? So realistically speaking, even though I have no doubts that the heat pump will help you out squeeze out the maximum range from an i3, it's not this magical thing which will suddenly give you 30-40 miles of extra range. On a funny side note, in terms of money, if we were calculating how much we saved by having the heat pump, on this particular trip it literally works out to about 3 pence. So not much of a difference, is it? Does that mean that we are saying that the heat pumps are pointless? No. In fact, quite the opposite, especially for household heating. We think heat pumps are a fantastic thing. You have to keep in mind, when you think about a house, your biggest consumer of energy is the heating system. So doing anything to improve the efficiency of that will have a massive impact on the overall consumption of the entire household. With a car, even though EVs get a lot of bad press for having worse range in the winter than in the summer, most of your energy expenditure is towards the driving. So you would need to make massive leaps in efficiency in the heating system for it to manifest itself in the overall driving range. This can generally be the case for some EVs. For example, Tesla Model 3s are known to be very efficient, especially with the heat pump, because they can scavenge heat and effectively move waste heat from the drivetrain into the passenger cabin. In case of the i3, the conclusion is very simple. Because you can't order new ones anymore, we wouldn't limit our search on the used market just based on the heat pump. At best, only about 10% of cars have them, especially with the prices of these cars equipped with the biggest 120 Ah battery having come down recently. There is really no reason to look for a 94 Ah specifically with the heat pump, because a 120 Ah even without the heat pump will far exceed the range of that vehicle, and generally speaking, for a couple of £1,000s more, you get an overall younger car with younger suspension and so on. Obviously, we will still keep stocking cars with the heat pump, so if it's something you really want, feel free to get in touch. In fact, if you're in the market for an i3, it's best to get in touch and we can send you our stock list, because a lot of our stock sells before it actually makes it onto Auto Trader, and the heat pump is still a nice bonus to have on top of all the other specification if you're looking for a highly equipped car. But keep that in mind, that at least in our eyes, especially with these big batteries, it's really not that necessary. And I think that's a good point to wrap up the video on. Thank you very much for watching. If you enjoyed it and if you appreciate the effort we put into the tests, hit the like button, because we generally speaking are not fans of driving somewhere just for the sake of testing. We really always try to tie it in with something else. But in these cases it's hugely weather dependent and we wanted to make sure that we use similar cars we have in stock. So we went ahead and did it just for you anyways. So thank you very much for the continued support. We will try to make more of similar tests in the future in different weather conditions to see whether there will be more of an impact on the overall range. So stay subscribed for that. And as I said, thank you very much for watching and see you in the next one.